Hello viewers, my name is Dr. Ajay, Department of ECE, Institute of Aeronautical Engineering, College, Hyderabad. Today we are going to discuss the topics fading, path loss and tropospheric scattering. So these are the topics which belong to the course Antennas, Waves and Propagation. The topics are fading, path loss and tropospheric scattering. Let us start our session today. So what is fading? So fading is basically undesirable variation in the intensity of signal received at the receiver. It means that whenever we are going to propagate a signal from the transmitting antenna, it is going to the receiving antenna. Reduction in the electric field strength at the receiver is known as fading. Reduction in the electric field strength at the receiver is known as fading. So fading, there are many reasons for the occurrence of fading between the transmitting antenna and the receiving antenna. Suppose if we are assuming, if we say 20 watts of electric power is radiated from the transmitting antenna and only 15 watts of power is going to reach to the receiving antenna. 30 watts of power is radiated by the transmitting antenna and only 15 watts of power is being received by the receiving antenna. It means that there is a loss of energy of 15 watts in the free space. There is a loss of 15 watts in the free space, that is the electric field strength. So here, this loss of energy, there are many factors which influence this loss of energy. There are many factors which influence this loss of energy and why this loss of energy is occurring and what are the various reasons for the reduction of field strength of the receiver we are going to discuss today. So which is related to the topic fading. So fading is basically the undesirable variation in the intensity of the signal received at the receiver. So any fluctuations in the received signal strength is due to variations in height and density of the ionization in different layers. So here we can, there are three modes of propagation as we know earlier. There is a ground wave propagation, sky wave propagation and space wave propagation. So fading is observed in all these propagations. So fading is common either in the for short distance communication or long distance communication, or in the ground wave propagation, or in the space wave propagation, or in the sky wave propagation. So these fluctuations of the signal in the atmosphere is common when we transmit the electromagnetic rays towards the receiver. So basically, the fading, it is the common characteristic of the high frequency short wave propagation, that is sky wave propagation. So fading is a common characteristic of high frequency short wave propagation, that is the sky wave propagation. So whenever we are going to transmit the electromagnetic waves towards the sky, these electromagnetic waves are reflected, some electromagnetic waves are refracted from the sky towards the receiver. So when these electromagnetic rays pass through different layers in the sky, some amount of energy is being absorbed by the ionospheric region and the remaining amount of energy is being reached to the receiver. So there are some characteristics which we need to discuss why there is a loss of energy in the sky wave propagation. There are many types of fading occurring due to the variation in the signal strength. That is, we can classify the fading in terms of duration of the variation in the signal strength. So fading is classified in terms of duration of the variation in the signal strength. So here there are rapid fluctuations. So these are due to multipath interference and occur for a few seconds. So these are due to multipath interference and they occur for a few seconds only. Suppose if I say, let us take, there is a transmitting antenna and there is a receiving antenna. So some waves will go directly towards the receiving antenna. Some amount of rays will reflect from the ground and they are going to interfere with the another path, that is the direct path. And some electromagnetic rays are going towards the sky and they follow multiple reflections like this and they reach to the receiver. So these paths are not permanent. So these electromagnetic rays paths are not permanent between the transmitting antenna and the receiving antenna. So these are due to multipath interference and they occur for a few seconds. That means that this path is going to interfere with the direct path and sometimes this path will be occurring, sometimes this path will be interfering with other electromagnetic rays. So this multipath interference, we call it as multipath propagation. And this multipath interference is only for a short seconds only, for a few seconds only. These type of fluctuations are known as rapid fluctuations. So due to rapid fluctuations also, the field strength is going to reduce at the receiving section. The second one is short-term fluctuations. The second one is the short-term fluctuations. So these are due to variation in the characteristics of the propagation medium, and they occur for a few hours. So these are due to the variation in the characteristics of the propagation medium, and they occur for a few hours. It means that suppose if I say the transmitting antenna and here there is a receiving antenna, the total distance is suppose let us say 5 kilometers, 6 kilometers. Let us say the distance between the transmitting antenna and the receiving antenna is 6 kilometers. If we divide this into two parts, 6 kilometers, here there is a 3 kilometers and here there is a 3 kilometers. Let us say we are going to transmit the signal. We are going to transmit the signal from transmitting antenna to the receiving antenna. So here when the signal is going to transmit from the transmitting and the receiving antenna, the signal is going from one region to the other region. Suppose here there is a heavy rainfall is there. Here there is a heavy rainfall. And here there is no rainfall. Here it is a dry. Here it is the cool. The temperature is cool. Why? Because there is rainfall. Here in this portion there is no rainfall. The weather conditions is very dry. It means that whenever this region we call it as cool region, it is a density. The density is more here, and in the dry region the density will be very less. Here the density will be very less. Here the density will be more. So as there is a change in the densities between one region to other region, definitely the velocity of propagation of the electromagnetic wave will be changing continuously. Hence there are some fluctuations happening for the electromagnetic rays which we propagate from transmitting antenna to the receiving antenna. It means that whenever we transmit the electromagnetic rays from one medium to other medium, definitely refraction takes place, and at the same time the velocity of propagation of the signal will also be changing. So due to these changes of whenever there is a change of velocity of the path, definitely there will be some delay in reaching the electromagnetic rays to the receiving antenna. So these type of changes of characteristics of the propagation medium are also responsible for reduction of field strength at the receiver. So these type of fluctuations are the rainfall will be for a shorter amount of time only. So the characteristics of the propagation medium will not exist for a long term, for many hours or for many days. So only for a few hours, that means either 2 hours or 3 hours there will be rainfall, and the characteristics of the propagation medium will be changing. So these type of fluctuations are known as short term fluctuations. Long term fluctuations, these are due to seasonal variations in the propagation medium, and they occur for a few days. It means that we know that there are 3 types of seasons we are having. One is the winter season, one is the summer season. So there are winter season, autumn season, and summer season. So we are having summer, we are having winter, we are having the autumn season. So in these 3 seasons, the speed of the electromagnetic ray differs. The speed of the velocity of the electromagnetic ray differs either in the summer or autumn season or winter. The speed of the electromagnetics will be very faster in the summer season. The speed of the velocity of the electromagnetic rays will be very less in the winter season, and the speed of the electromagnetic rays in the autumn season will be moderate. So accordingly, we need to take decisions wisely whenever we are going to transmit the signal, whether we need to transmit the high frequency signal or low frequency signal, and we need to change the frequency according to the seasons. We need to change the frequency according to the seasons so that the complete signal is going to reach to the receiver. So here, this type of fluctuations are for around 3 months or 4 months. That means this type of variations occur for 4 months or 3 months. So these are due to seasonal variations. That is, the characteristics of the propagation medium occur for a few days only. So these are the classification of fading. There is a rapid fluctuations, short-term fluctuations, and long-term fluctuations. At receiver, the strength of the signal received is the vector sum of the waves received. So we know that whenever we transmit the signal here, these electromagnetic rays will pass in different paths. So here it will like this. Let us say this as electric field strength E1, and some waves are reflected here. This is E2, and some waves are going directly. This is E3. So this is the transmitting antenna, and this is the receiving antenna. So the total electric field at the receiver ER, it is given by all the vector sum of all the waves received by the receiver. That means E1 plus E2 plus E3. So because the waves leaves from the transmitter at the same time but reach the receiver through different paths. Here you can observe here in the figure, the E1 path and E3 path and E2 path are different. That means the distance of propagation between the transmitting and the receiving E1 path is more compared to the E3. The path of E3 is very less. The path of E3 is very less than E1. The path of E2 is greater than E3. The path of E1 is greater than E2. So like this, there are different paths. The waves are traveling from transmitting antenna to the receiving antenna. So the fading is also caused due to interference between the two waves of different path lengths. So here the E1, E3 and E2 path lengths are different. So if the path length is more, then there will be some delay in reaching the electromagnetic ray to the receiver. So one ray will be going at a faster rate, and one ray will be moving to the receiver with some delay. So due to this delay, due to these changes of velocities of the electromagnetic rays in different paths, these waves are going to interfere with each other. So due to this interference also, the signal strength is going to reduce at the receiving antenna. So there are different types of fading we are having as per our classification. So not only classification, we can also describe the fading in terms of different types. One is the selective fading. So it affects the different spectral components of radio signal with the different amplitudes. Hence the name is given as selective fading. So here it affects the different spectral components of a radio signal with different amplitudes. So whenever there is some abnormal, whenever there is some interference between the transmitting and receiving antenna, definitely there will be an effect of amplitudes of the different electromagnetic rays will be slightly reducing when they are going to reach to the receiver. So it affects the different spectral components of the radio signal with the different amplitudes. Hence the name selective fading is given. When the signal bandwidth is greater than channel bandwidth, the selective fading is given more importance. So the coherence bandwidth, what is the meaning of coherent bandwidth? So it is a statistical measurement of the range of frequencies over which the channel can be considered flat, or in other words, the approximate maximum bandwidth or frequency interval over which two frequencies of a signal are likely to experience comparable or correlated amplitude. The selective fading, it is more dominant on high frequencies for which sky propagation is used. So the selective fading is given more significant at high frequencies for which the skywave propagation is used. The selective fading produces a serious distortion of the modulated signal. That means the fading is frequency selective, hence the portion of frequency adjacent to the frequency of signal also fade independently. So selective fading generally occurs in the skywave propagation only, and whenever we are going to modulate the signal of the transmitting antenna, and this modulated signal when we send towards the sky, definitely there will be some portion of interference of frequencies with the adjacent component frequency of the signals, and then the signal will fade independently in the atmosphere. So it is more dominant at high frequencies for which the skywave propagation is used. So due to selective fading, the amplitude modulated signals are seriously affected. The AM signals are more distorted due to selective fading rather than SSB signals. So whenever we are going to modulate the signal, either AM, FM or SSB, AM signals are more distorted when we transmit the signal to the skywave propagation. So whenever we are going to propagate the signal towards the sky, SSB modulation is preferable than AM modulation. Hence, to reduce the selective fading, a single sideband system can be used. The second one is interference fading. As the name indicates, it is fading produced because of upper and lower rays of the sky wave interfering with each other. So this is the most serious fading. So whenever the ray is going to propagate from the transmitting antenna to the receiving antenna, in the sky wave there are different layers: D layer, E layer, and F layer. So this ray will go enter into the D layer, and it will enter into the E layer also. So there are different, the same ray is traveling in the different layers in the different paths. So this is the most serious fading. This is the most serious fading. That means the upper and the lower rays of the sky wave are interfering with each other. The upper and the lower ray are interfering with each other like this. So the rays are propagating in different number of hops. The rays are propagating in different number of hops. Hence, whenever these rays interfere, definitely there will be some delay in reaching the rays to the receiver. You can see here, this is the transmitting antenna and this is the receiving antenna. Some rays will go from the earth like this, from the towards the sky. So there are different paths. In different paths, the electromagnetic rays are passing to the receiver. Here, the 3 paths and the 2 paths on the ground and in the sky are interfering with each other. So these waves are traveling in different paths towards the receiver. So there will be some delay in reaching all these paths to the receiver. So due to the interference, the signal gets faded, and hence the total amount of field strength at the receiving antenna will be reduced. So because of these conditions, the amplitude of the resultant also varies continuously. So due to the multipath interference, definitely the amplitude of the ray, the amplitude of the electromagnetic wave at the receiving antenna will be reducing. So this can be minimized by using space diversity or frequency diversity reception. Absorption fading. This type of fading occurs due to the variations of single strength with the different amount of absorption of waves absorbed by the transmitting medium. So absorption fading, this type of fading occurs due to the variations of single strength with the different amount of absorption of waves absorbed by the transmitting medium. So there are different types of molecules and gases present in the atmosphere. These gases and molecules are different from one area to the other area. So the absorption will also be different when we transmit the signal from one area to the other area. Polarization fading. So whenever the sky wave reaches after the reflection, the state of polarization is constantly changing. So whenever, if you say the transmitting antenna is going to produce circular waves, and when these circular waves hit any obstacle here, when these circular waves hit any obstacle here, the state of polarization, that is, there will be some, the wave orientation, the wave direction will be changing. It means the circular polarization will be becoming elliptical polarized waves after striking the obstacle. So whenever the circular polarized waves strike any obstacle, definitely these circular waves are converted into elliptically polarized waves. That means the wave direction is going to tilt its direction. That is, the orientation of electric field will be varied. So as there are more number of obstacles, definitely the state of polarization, the state of the direction of the electric field will be changing continuously. So here, this is one of the reason for the reduction of field strength at the receiver. So the polarization of the sky wave coming down changes because of the superposition of the ordinary and extraordinary waves, so which are having random amplitudes and phases which are oppositely polarized. So whenever these electromagnetic waves are going to transmit to different layers in the, this is transmitting antenna, this is receiving antenna. So whenever D layer, E layer, F layer, F1 layer and F2 layers are there in the atmosphere, so whenever we transmit the signal towards the D layer, when it touches the D layer, the state of polarization changes, the direction of the E field will be changing. It will be coming like this and will go and reach to the receiver. This is one path. Similarly, whenever the signal is going to touch the F1 layer, it reaches to the E layer, again it goes to the F2 layer, again it comes to the receiving antenna. So like this, there are some ordinary and extraordinary waves propagated within the layers with the different amplitudes and different phases. So the state of polarization depends upon how many number of stages the electromagnetic ray is passing, how many number of levels or how many number of obstacles the electromagnetic ray is going to touch, or it is going to pass under different stages or different layers. The polarization will be changing continuously. The polarization is changed, definitely the amplitude and the phase of the electromagnetic wave will be changing. Definitely there will be some field strength reduction on the receiving antenna. Thus, the polarization of the wave changes continuously with respect to the antenna, which gives rise to the variations in the amplitude at the receiver. So, such type of fading is called as polarization fading. Skip fading depends upon the skip distance. Suppose let us take one example, the transmitting antenna and the receiving antenna. We are going to transmit a 25 megahertz signal. Suppose the transmitting antenna and receiving antenna, the distance is very less. As we are transmitting the very high frequency signal, we need to place the receiving antenna exactly where the transmitted signal is going to reach to the receiving antenna. That means the transmitting antenna, when it propagates the signal into the sky, after multiple number of reflections and refractions, the signal is going to reach to the receiving antenna. So we need to place exactly at that location where the signal is going to touch the surface of the ground. So where the receiver signal is going to touch the surface of the ground, exactly at that location, we need to place the receiving antenna. Suppose if we don't place the receiving antenna exactly at a location where the receiving signal is going to get, then the signal will be going beyond the receiving antenna. The signal is going to reach beyond the receiving antenna. That means the signal is going to skip from the receiving antenna. So due to the variations in the height and the density of the ionized layer, the point at which the wave can be received moves in and out of the skip zone. So thus, due to this, the amplitude of the receiver also varies, producing a skip fading near the skip. So exactly, we need to know where the signal is going to reach, where the wave can be reached exactly on the ground. So at that point only, the receiving antenna has to be placed. So if at all we place the receiving antenna beyond the point, or in the point, or above the receiving point, then the signal will not going to absorb by the receiver. That means the signal is going to skip beyond the receiving antenna. In such a case, definitely the amplitude of the receiver varies, producing a skip fading near the skip. So these are the different types of fading we have seen: the selection fading, absorption fading, skip fading, interference fading, and polarization fading. So let us come to the next topic, that is the tropospheric scattering. Let us come to discuss the next topic, that is the tropospheric scattering. The scattering of energy, whenever we propagate the signal into the sky, there are different types of gases and molecules in the atmosphere. So due to this, the electromagnetic rays, when these touch the molecules and gases, they scatter in different directions in the tropospheric region. So tropospheric region, it is a distance of 16 kilometers above the surface of the earth. We call it as a tropospheric propagation. So in the tropospheric layer, we propagate the electromagnetic signal. The signal will be scattered. The radio waves will be scattered in different directions. So the scattering of energy in a radio wave occurs in the tropospheric for a wide range of frequencies between 400 to 5 gigahertz. So whenever we transmit the 400 to 5 gigahertz signal into the tropospheric region at a distance of 16 kilometers, so definitely the energy will be scattered in different directions. So the amount of scattered power depends on the magnitude of variations of the refractive index and on the distance over which the variations occur. So above 16 kilometers, definitely the temperature will be reducing. So here we can see here from the surface of the ground that as we increase the height, the temperature will be increasing to a certain height, and after 16 kilometers the temperature will be reducing, and above 16 kilometers the temperature again will be increasing. So like this, there are many layers in the atmosphere where the temperature will be increasing and decreasing. So here the amount of scattering power depends upon where the signal is going to propagate in these layers, or whether the signal is going to propagate touch in this layer, or whether the signal is going to touch the tropospheric layer. So definitely there will be change in the refractive index. There will be change in the magnitude of the variation of the refractive index over which the variations occur. The field strength at large distance normally fall off at a rate of 0.1 to 0.2 dBm. So here, whenever we transmit the signal into the tropospheric region, definitely there will be some loss of energy at a rate of 0.1 to 0.2 dB per meter. So 0.1 to 0.2 dB per meter is the most common fall of energy when the signal is going to propagate from the transmitting antenna to the receiving antenna. The waves diffract blend around the curved surface of the Earth. So we know that the curvature of the Earth is the surface of the Earth is never flat or curved. At some areas the Earth will be flat, and at some areas the Earth will be curved. So whenever the wave touches the curved surface, the wave is going to bend and propagate in a forward direction. I'm going to propagate in the forward direction with a different state of polarization. So the roughness of the Earth decides the strength of the diffracted field in the shadows. Field in the shadow region is greater. Great Earth is rough. So here, some areas the Earth is regarded as flat. At some areas, the Earth is regarded as rough. So how much bend is occurring, how much amount of loss of energy is occurring, it depends upon the roughness of the Earth, or it depends upon the smoothness of the Earth. So this diffraction scattering is not common in all areas. The scattering and diffraction depends upon the smoothness and the roughness of the Earth. Secondly, there are eddies and bobs in the atmosphere due to turbulence, which cause discontinuities and disturbances, giving rise to small irregularities in the refractive index. So there are many eddies and blobs, formation of blobs and eddies occurring in the atmosphere due to the temperature variations and due to the big industries and factories, due to the fog coming out from the big industries, due to the fog coming out from factories. Blobs and eddies are formed in the atmosphere due to the clouds and due to the turbulence, which causes the discontinuities and disturbances, giving rise to small irregularities in the refractive index. So blobs and eddies are also responsible for change of refractive index. So if the refractive index is changed, the velocity of the signal changes. Definitely, there will be some discontinuity and disturbance occurring in the amplitude of the electromagnetic wave signal. Hence, the rays passing above the troposphere are scattered to points in the shadow zone. So there is in this figure you can see here the transmitting antenna and the receiving antenna. So whenever these electromagnetic rays enter into the tropospheric layer, these are going to scatter. Here you can see here the shortest path here. This is the shortest path, and this is the longest path here. So whenever this going to enter in the tropospheric region, these are going to scatter in different directions. These are going to scatter in the different directions. And this is known as the forward scatter. And here some electromagnetic rays are escaped into the free space, where no reflection is going to take place. So totally the tropospheric scattering, it depends upon the nature of the atmosphere. It depends upon the nature of the atmosphere. The nature of the atmosphere is not constant at all times. The third and final cause is that even in the standard atmosphere will produce small reflections that scatter energy into the shadow zone. The signal level has seasonal variations of about 10 dB. A loss of 10 to 12 dB occurs due to fading. So in every season, that is the summer season or winter season or autumn season, there will be loss of variation of 10 to 12 dB due to fading. So the tropospheric scatter mode of propagation is most effective for the ranges of 350 miles. Is more effective for the ranges of 350 miles. So the tropospheric scattering occurs whenever you're going to transmit for long distance communication around distance of 350 miles. So when we propagate the signal 350 miles, there will be a loss of 10 to 12 dB in the propagated electromagnetic wave signal. Let us discuss the structure of atmosphere. So in the radio wave propagation, the Earth's environment between the transmitting and the receiving antennas play a very vital role. So whenever we are going to transmit the signal for short distance communication, the loss of energy will be very less. At the same time, the loss of distance will be the loss of energy will be more when the distance of communication is increased. So the atmosphere is one of the reason for this loss of energy. So the atmosphere of the Earth mainly consists of three regions, namely troposphere, stratosphere, and ionosphere. So the total atmosphere can be divided into three different regions. One is the tropospheric region, the second one is stratospheric region, and third one is ionospheric region. Now let us discuss how much amount of path loss occurs when we transmit the signal between the transmitting antenna to the receiving antenna. So whenever we are going to transmit the signal from the transmitting antenna to the satellite, how much path loss occurs? So whenever we transmit the signal from the Earth station to the satellite, how much amount of path loss is going to occur? Let us derive an expression. Here E is the Earth station. Here there is a satellite here, and the total distance between the Earth station and satellite is denoted as a D here. And from the satellite towards the center of the Earth, we are going to consider this as H plus A. The total distance is H plus A, and A is the radius of the Earth. Here A represents the radius of the Earth, and here A is represents the radius of the Earth. So here you draw a line from E, a perpendicular line directly. You draw a perpendicular line here from E. Let us assume this as 90 degrees, and this angle as beta. This angle as beta. Okay, so here from the we know that there is a cosine rule. We know that from the cosine rule we can write so here there is a diagram is represented here. Angle SEO you can write as beta plus angle SEO can be written as 90 beta plus 90 here. So cos SEO can be written as cos 90 plus beta. This is equal to minus sine beta. Okay, and from this here from this figure we can also write the cosine rule formula. SO square is equal to SO square is equal to EO square plus ES square minus 2 into EO into ES into cos angle SEO. So from this figure we can write SO square is equal to EO square plus ES square minus 2 into EO into ES into cos angle SEO. Cos angle SEO. So what is EO here? We can write as A square. And here ES square can be written as D square here. A square plus D square. Minus 2 into what is EO in the figure? It is A. And ES is D. And cos angle SEO, it is given as cos 90 plus beta. Cos 90 plus beta. So here the angle SEO can be written as beta plus 90. So based upon this equation, what is SO square? SO square is nothing but H plus A whole square from the figure. H is the height from the surface to the satellite, and A is the radius of the Earth. So H square, this can be written as H square plus A square plus 2AH. H square plus H square 2H is equal to A square plus D square minus this is plus 2AD sin beta. So cos 90 plus 0 is equal to minus sin beta. Minus and minus plus. So 2AD sin beta. So here A square, here A square get cancelled. So we can write H square plus 2AH is equal to D square plus 2AD sin beta. And if we substitute the values, so this is a quadratic equation. A plus H whole square is equal to H square. We can write this as D square plus You write in the form of a quadratic expression. You can see here the quadratic expression d can be written as d square plus 2ad sin beta minus a plus h whole square plus a square. So here this is a quadratic expression, a square plus 2ab plus b square. So we can solve this expression by finding the value of d, the distance, that is minus b plus or minus root of b square minus 4ac by 2a. So here a is equal to 1. What is b? B is equal to 2a sin beta, and c is equal to minus of a plus h whole square plus a square. Minus of a plus h whole square plus a square. So we are going to substitute these equations, these terms a, b, c in this value, and simplify the mathematical analysis. You will get the value of d. A is equal to 1, b is equal to 2a sin beta, and c is equal to minus of a plus h whole square minus a square. So here d is equal to, we can write minus b plus or minus root of b square minus 4ac by 2a. So let us substitute all this and simplify. You will get minus 2a sin beta plus or minus square root of 2a sin beta whole square plus 4 into 1 into a plus h whole square minus a square, and d is equal to minus 2a sin beta plus or minus root of 4a square sin square beta. So if you substitute here 4 into a plus h whole square minus a square here. So we shall further simplify this, minus 2a sin beta plus or minus root of 4a square sin square beta here. So if we substitute this simplification, you will get a square plus h square plus 2ah minus a square. So minus a square plus a square get cancelled. So substitute here 4 into 4h square plus 8ah you will get. So if you simplify here, you will get the value of d as minus 2a sin beta plus or minus 2 into root of a square sin square beta plus a plus h whole square minus a square. So let us take as distance is always positive. Distance will never be, distance is not negative. So distance is only the positive. So we are going to consider only the positive value. So minus a sin beta plus root of a square plus sin square beta plus a plus h whole square minus a square. Now further simplification, you will get a square sin square beta plus a plus h whole square minus a square minus a sin beta. So sin square beta means 1 minus cos square beta plus a plus h whole square minus a square minus a sin beta. Let us further simplify as multiplying with a square. So a square minus a square cos square beta plus a plus h whole square minus a square minus a sin beta. So if you simplify here, a square get cancelled. You will get a plus h whole square minus a cos beta whole square minus a sin beta. So d is equal to square root of a plus h whole square minus a cos beta whole square minus a sin beta. And from the figure, you can observe here, this is the beta value. The distance is minimum when this is 90. So when beta is 90, the distance is said to be minimum from the figure here. This is beta here. D is equal to root of a plus h whole square minus a cos 90 whole square minus a sin 90. Substitute the beta value as 90. So you will get a plus h whole square minus a square minus a. So simply d is equal to h. So d is the distance between the satellite to the transmitting antenna is nothing but the height from the surface of the earth to the satellite. And the distance is maximum when beta is 0. The distance is maximum when beta is 0. So d is equal to square root of a plus h whole square minus a cos 0 whole square minus a sin 0. So here there is a 0 here. The substitute beta value is 0. And we know that the radius of the earth is 6378 kilometers. 6378 kilometers, the radius. And height, it is 35,835 kilometers. And if we substitute these two values here, height of the satellite from the surface of the earth, we will get the d is 41748.58 kilometers. We get the value of d as 41748.58 kilometers. So d is the distance of propagation. Now the maximum distance for the geostationary orbits. So we need to indicate the path loss by the value of Ls. We need to indicate by this path loss as Ls. The path loss occurs through spreading of signal energy through the space, and the spatial loss is given by Ls is equal to 32.45 plus 20 log d base kilometers plus 20 log f in megahertz. So the path loss calculation, it depends upon the spatial path loss of the signal loss of energy is given by Ls of dB is equal to 32.45 plus 20 log d base 10 plus 20 log f base 10. So here log d and log f. F is the frequency and d is the distance of propagation of the signal. So where d is given by 41,748.58 kilometers. And here is the spatial path loss. So this is a small derivation about the path loss. Just we have calculated the value of d from this equation. So d is nothing but depends upon the value of beta. That is the beta, whether the signal propagation is the path length is less or path length is more. The path length is vertical or path length is slant from the surface of the earth. So just we have taken a figure here. Just we have represented this as an earth station here. This is an earth station. We are going to transmit the signal from the earth station. This is the earth station. We can transmit here, and this is going to reach to the receiving point antenna here, center of the earth. At the center of the earth, we are going to place a receiving antenna here and join these 2 points. This is the radius of the earth, and this is the radius of the earth, and this is the height of the signal. Height of the signal here. And let us take a point here. This is the beta, and this is the 90. Let us draw a perpendicular line from this point, which indicates as 90, and this length is beta. So depending upon the value of beta or depending upon the value of angle, the distance of signal from the earth station to the transmitting and to the satellite is going to depend. So this angle is very crucial for determining the distance, of propagation of the signal from the earth station to the satellite. So these are the topics we have discussed today. That is the fading, that is the structure of atmosphere, and also the path loss calculations, the tropospheric scattering. So tropospheric scattering is nothing but we are going to propagate the signal towards the sky at a distance of 16 kilometers, where scattering of electromagnetic rays is going to occur due to the different eddies and blobs in the atmosphere. So due to the presence of more eddies and blobs in the atmosphere, the density will be changing continuously. Definitely there will be change in the phase and amplitude of the electromagnetic rays before they reach to the receiving point here. So if you want to refer for reference of this topic, so that is the tropospheric scattering and fading, and also the structure of atmosphere, the structure of tropospheric scattering, the fading, the topic of fading, the structure of atmosphere, and the path loss calculation. So all this you can refer the Balanis textbook here. You can also refer the Bakshi textbook. You can also refer the KD Prasad textbook for these topics. There is the path loss, there is the Balanis, the tropospheric scattering, the fading, and the structure of atmosphere. So let us close the session today. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.